during the first part of this lecture, I have tried to analyze quantum ideas in qualitative terms. I have insisted upon the fact that in an experiment you have to specify the apparatus you are using, that there are some quantities that you cannot measure simultaneously, getting precision on one at the expense of the other. One example was the position of a particle in a Young double slit and the phase of the wave function on the screen. I showed these ideas in a qualitative way by calling it complementarity, Heisenberg uncertainty relations. Now I would like to describe the formalism which has been developed between the year 1925 and 1930, which has expressed by precise mathematical equations what Bohr had semi-intuitively stated with the concept of complementarity. I will recall the formalism, the very elegant formalism introduced by Dirac, which described quantum states as vectors in an abstract space. It's called the Hilbert space. And the physical observables, the quantities that you measure, are represented by operators which act on this space. They are called Hermitian operators, and I will tell you what it means. It's operators which have a spectrum of real eigenvalues, which I will also explain. And we then enunciate the postulates of quantum measurement. The position, momentum, and energy operators of a particle will be described as the generators of the translation in momentum in space and in time of the quantum state. And I will also try to explain that this approach gives a deeper meaning to the ideas which I have discussed before, and which allow us to reanalyze quantum interference experiments and complementarity in quantitative terms. But before going to that, I would like to remind you very simple things about ordinary real vector spaces, the vectors that we are all used in classical physics. As you know, a vector can indicate a position in space, it can indicate a velocity, an acceleration, a force, and these vectors in real space are combined according to rules which we all use intuitively. I recall you here a few rules. Addition of vectors, so you construct a parallelogram and the sum of two vectors is shown here, a plus b. Vectors can be multiplied by real numbers. It has a very clear meaning. What if you have vector a, what 2a means, 3a means. So you can multiply a vector by real numbers, and you can make linear combinations of vectors. So you can add vectors, multiply them by a number, combine them in a classical way. You can also define the scalar product of two vectors in a Euclidean space. What is a scalar vector? It's you take a couple of vectors and you associate a number, a real number, which is called the scalar product. And this scalar product is commutative. A dot b is equal to b dot a. So this is also something very well known. And you have a distributivity of all this. I have shown you at the bottom the scalar product of alpha A with beta D plus gamma C. You can develop this expression as you would do with numbers. So you can, all this is commutative and distributive. You can also represent a vector with these coordinates in a basis of vector states. I show you here in ordinary space. You can define a basis of three orthogonal vectors E1, E2, E3. By orthogonal, I mean that the scalar product of two of them is 0, and the scalar product of a vector with itself, EI is equal to 1. So it's orthonormalized. And this basis allow you to develop any vector on the basis. The coordinates of a vector A are the scalar product of A with the basis vectors. And so you have a very simple way of expanding any vector on the basis of states, and the coefficients Ci are real numbers, real coordinates. You can also perform linear operation in vectors. If you take a vector, you can rotate it in space, and the rotation described by a matrix. I'll give you the formula there. And the coordinates of the rotated vector are linear combination of the coordinates of the initial vector, and these combinations are given by a matrix which has a dimension d by d, where d is the dimension of the space. So all this is quite usual in ordinary geometry. So I show you, for instance, here the formula which gives the coordinate of the rotated vector as a linear combination of the coordinate of the initial vector. Another point I would like to make also is that when you make this kind of transformation, rotation in vector, the product of two rotations is not always commutative. For example, here I take a first example. I make a rotation around the same axis. I make a rotation of angle alpha around z, and then beta around z. If I do that, it's commutative. I can rotate first by angle beta, then by angle alpha, or the opposite. So two rotations around the same axis commute. On the other hand, if you take two rotations around different axes, they don't commute. And I give you here a very simple example. I do a rotation around z by angle pi over 2, followed by a rotation around y by pi over 2. Be careful in this order, because I will apply this transformation to a vector that I will write here. So the first rotation around z, then around y. And I show you what happens. If I take a vector which is around z, along z, rotation around z does not make anything. And then the rotation around y, rotate it, and in the end, the vector finishes around x. But what happens if I do the operation in the reverse order? You see, if I start by the rotation around y, I bring this to this position, and then rotation around z, bring it here. So you see that the product of these two rotations depend on the order in which I do them, and the rotation do not commute. And this will have a very important consequences in quantum physics, because as we will see, rotations are generated by angular momentum components. So the fact that the rotation don't commute will entail the fact that components of the angular momentum do not commute, which means that you cannot measure them simultaneously with precision. And this is related again to the uncertainty relations. So you see how geometry intervenes in quantum physics to lead to these very important properties. So now that I have recalled what happens in real space, I will go to the space of states in quantum physics. So these are postulates. In fact, you cannot demonstrate them, but you make these postulates and they form a set of postulates which allow you to do all calculations. And the validity of the postulates are confirmed by the fact that all that you calculate with them corresponds to what you can do in experiments. So the first point is that any state in quantum physics of a isolated quantum system is represented by a vector in a Hilbert space. And I will precise what it means. And the vector in classical geometry, you mark a vector by an arrow on top of it. In quantum physics, you put the symbol of the state in a bracket like that. So this is notation by Dirac. So a state is defined in this way. Psi, which means that psi specifies the state as we will see in a minute. Any linear combination of, and it's called a ket. It's not called a vector, it's called a ket. And any linear combination of kets is a possible ket, exactly like in vector algebra. The difference is that the coefficients now are complex numbers. It's no longer real. It can be real, but it's more generally any combination of complex number which multiply kets is a possible ket. And these coefficients are called probability amplitude. And in fact, they are the amplitude which give rise to interference effects. When you multiply two complex numbers, the phase matters in the result. Okay. To any ket, now the point, we have to define what is a scalar product. And this is a little bit more tricky than in classical geometry, because the scalar product in the Hilbert space is not commutative and it's not real. So in order to define the scalar product, what you have to do is to associate to each ket, you associate another symbol where you have inverted this, the symbol of the ket, and this is called a bra. The bra, in fact, it's different from a ket. The bra is an application which, when it's acting on any ket, will give you a complex number. So I have tried to show you here. If you apply the bra is a function which images any ket phi onto the body of complex number. So psi applied to phi give a complex number which is not a psi phi. So you make the product, but you be careful that the order counts. This is the scalar product of the bra psi with a ket phi, which is different from the opposite as we see in a moment. So it's a complex number. So this C number is analogous to the scalar product of two vectors, but the difference is that the inner product, which is also called, it's called a Hermitian product. So it's an inner product because it's a product of two vectors of the space, which gives a number. This inner product is a complex number, and I will discuss the physical meaning later. This complex number is, if you change the order, you replace the number by its complex conjugate. Now, remind you the complex conjugation, you change the sign. This number is a complex number A plus IB, and you change the plus I into a minus I when you change the order. So it's a scalar product, which is a complex number, and we change to the complex conjugate if you change the order. This means that the correspondence between kets and bra is antilinear. If you take a linear combination of the kets, the corresponding bra is the same combination, but with a complex conjugate. So you have to get used to that, but the rules are very simple. When you want to invert a formula, you have to replace all the complex number by the complex conjugates, and we give the rules for the operators too. So this is simple. In analogy with ordinary vector, two states are orthogonal if the inner product is 0, and a state is normalized to unity if its scalar product with itself is equal to 1. So this is exactly the same thing that for ordinary vectors. Now, let's look at what is a projection. In ordinary space, when you project a vector on an axis, the length of the projection is a scalar product, and the result is in the direction of the axis. You project a vector. Here, it's the same thing. When you project the vector psi on phi, you have a complex number, and it's along phi. So this is the projection of psi on phi. So it's a vector along phi whose amplitude is given by this. And you see that it is as if you had multiplied psi by this symbol, a ket with a bra against it. And this symbol is an operator. It's something which takes a vector and changes it into another vector. So it's a transformation in the space, which is an operator. And it's called a projector because it projects psi and phi. And you see that projectors are just a ket attached to a bra in this way. So this notation by Dirac is extremely elegant because you will see that once you get used to it, you do calculation without having to remember. You have to remember the rules, but it's obvious. So what I have written here, this projector Pi is a linear operator. Why it is linear? Because if you have the sum of two vectors you project, you will get the sum of the projections. And any linear combination will give you the same linear combination in the projection. So it's a linear operation of the Hilbert space, which transforms any state into a state collinear with phi. So it's analogous to the projection on a vector basis. And if you are in a space of dimension D, you can define a set of D vectors which form a basis exactly like in ordinary space. Instead of 3, you can have 2, 3, 4, an infinite number of states depending upon the dimension of the Hilbert space of your problem. And on the next slide, I show you how you project on a basis. So how do you define a basis? The basis vector have to be orthogonal and normalized. So phi j is equal to delta ij. Either I is equal to j, you get 1, or I is different from j, you get 0. This is exactly the same as in ordinary space. And now the sum of the projectors on all the phi gives the identity, because you can, if you have any vector, if you project it on all the vector of the basis and make the sum, you find your vector. This is the definition of the representation in a given basis. So very important rule, the sum of all the projectors is equal to 1. This is called the closure relationship. If you take a basis, you sum the projector on all the basis of the projector of the basis, and you find the identity. And of course, any state can be developed on any basis of orthogonal state, exactly like in the ordinary vector space. And if a change of basis is just a rotation, and here is a generalization. You can change of basis and you have a different representation of the same state. Now, starting from that, you can define operators. An operator is something, it's an operation which will transform a vector into another one, like a rotation in ordinary space, for instance. So you see here, how do you define an operator A? What you can do is you can sandwich A between two identity operator, I on the left and I on the right. So I have not done anything if I do that. But now, on the left, I is a sum over the basis of all the projector I, and on the right, I have a sum on all the j of the same basis. And when I make the product, I get sum over ij of the ket I bra j time aij, where aij is a matrix. So you have a matrix representation now of any operator in any basis. A is a matrix, A d by d, where d is the dimension of the state. And these are the kind of matrices which Heisenberg introduced in his own description of quantum physics. So you see, I let you do that with the notes, but you see, now you can immediately write what is the action of A and ket psi. You introduce, you have just to introduce the closure relationship on the left and on the right, and you find this expression very easily. You can expand any vector, the product of what happens on a vector when A acts on it. You can find the new coordinates in terms of the old one exactly by the equation of matrix transformations. Now, what are eigenstates and eigenvectors? It's a very important notion. In fact, it's the central notion here. What you call an eigenvector of an operator in general, it's a vector which remains in the same direction when you act the operator on it. So it's what I have written here. You have a vector, you have the operator A acting on the ket A, gives lambda A, where lambda is a complex number, any number. This is, by definition, the eigenvector, and lambda is the eigenvalue. So this is true for any operator, but there is a class of operators which are very important, which are called the Hermitian operators. And I will try to define them here. What is, so you take an operator O, what is the adjoint of O? The adjoint of O is, this is the equivalent of a complex conjugation for operators. What you do is that you take you take the transpose of the operator, that is, you change. When you write your matrix, which is like a square, you take the one corner and you put it in the other corner, and you take the complex conjugate. So it's called the complex transpose of matrix, and it's called the Hermitian conjugate. This is the adjoint operator, and you represent it by cross, which is equivalent of the complex conjugation. Now, you have a very important class of operators, which are their self-adjoint. When you do that, you get the same matrix. These are called Hermitian operators. And this is the equivalent of real numbers, because you take the adjoint and you find the same number. So it's a generalization of real numbers. These are the Hermitian operators. And what is real? What is real is a diagonal. The diagonal is, of course, real. And for Hermitian operator, what happens is that you can always find a basis in which they are diagonal, and their elements of the diagonal are real numbers. And these real numbers are called the eigenvalues of the operator, because if you are in this basis, and if you have this operator acting on a vector basis, you find a real number. And these real numbers are very important because they are the result of measurement. A measurement is a real number. And so you need Hermitian operators. And the spectrum of the Hermitian operator is the value of their diagonal elements in a basis in which they are diagonal. So the only rule we have to remember is that an Hermitian operator is an operator which has a basis in which, of course, it is diagonal, and which has real eigenvalues, real matrix element on this diagonal. So in this basis, how do you write your operator? O acting on the eigenvector give you a real number times the vector. And so you can write the operator as a sum of projectors with real coefficients. Now this is different. It's a sum of projectors with real coefficients. And you see that I have used I to specify the eigenvalue. And I have another parameter alpha, because it may happen, and we will see that it happens often, that a given eigenvalue is degenerate. There are several vectors which have the same eigenvalue, several physical states which have the same eigenvalue for a measurement. So the most general expression for a Hermitian operator in its diagonal basis is like that. It's a sum of projectors with real coefficients. And this is just a diagonal element, which is a real eigenvalue for this operator. Okay. So now we are ready to enunciate, to discuss the measurement postulate. So do it carefully because it's important. When you perform, so to each quantity that you will measure in quantum physics, there is an observable O, which you can define. And when you measure this observable O on a system which is in the state psi, the result is one of the eigenvalues of the observable. And the probability to find it is obtained by this expression. That is, you put psi in between, you put all the projector on the subspace which has this eigenvalue. So sum over alpha, the I alpha, this is a subspace of all the states which have the eigenvalue AI, and you take the average value, you take the average value of psi in this state. So if you express this, you find this expression. It's the scalar product of psi with I alpha, sum on all squared and sum on all the alphas. And this is the probability. This is the probability to find the result AI when you make a measurement of the observable. And of course, the sum of all the probability has to be equal to 1, which means that the states that you are on which you make the measurement, you have to normalize the state in the invert space. The state is defined up to a length, up to a norm, and you have to choose the norm so that the system has a norm equal to 1. So this is a postulate. And you see this postulate means that when you make a measurement, you don't know what result you will find. You can only compute the probabilities to find a given result. Another postulate, which is very important, immediately after the measurement, the system collapses into the projection on the measured subspace. So you see, after the measurement, you have no longer the state psi, you have the projection of psi on the result of the measurement. And you see, this is something which is not deterministic, because before the measurement, you don't know where you will fall. You know only the probabilities, but once it has happened, you find the final ket, and this is something which is, of course, random and not reversible. All the information which was outside the measurement space is lost. So it's called this change, this instantaneous change of the wave of the state upon measurement is called sometimes the collapse of the wave function, the collapse of the state. And if you repeat the measurement immediately afterwards, you find the same result, of course, because the measurement has projected the state into the eigenspace. And so it means that if you remeasure, you will find, of course, the same result because the projection is already done. And if you do it second time, you will find the same result. So you can repeat a measurement, provided you don't let the system evolve between the measurements, you find always the same result when you repeat. Now, what can we do about, what can we say about interferences? Suppose now that the system that you measure is a superposition of states with Ci numbers. How will you compute the probability? You just plug this into the initial formula, and you find now that your probability arrives like that. And you see now that you have products of amplitude. If two states, I and j, can project on the same state, and if they are affected by coefficients, the product of these coefficients intervenes in the probability. And it's exactly what happens, for example, in the Young double slit experiment. You have the two passes, you have an amplitude for each pass, and the probability to find the particle at one point is a product of these amplitudes, which depend upon the phase difference between the two passes, and you get the interference at this point. Another important formula here. What is the mean? What does it mean by mean value? So you make a measurement, you find one result. If you start and do the experiment again with the same initial system, you will find another result because you have a probability distribution. And if you do a lot of measurements, the average value of all this measurement is what we call the mean value. And the mean value is obtained by this formula. You have to take the probability and multiply each probability by the result that is given by this probability. And if you write it this way, you recognize here the operator itself. So you see that the mean value is just the value of the operator in the state psi. That is the matrix element of O in state psi. This is the mean value. The last, I think, about the last point I will discuss now is what happens if you measure two observables, and it's very different whether they commute or not. So I will start by considering what happens if you measure two observables which commute. I will give you an example. If you take one particle, its position along an axis x commute with the position along another axis y, and commutes with the position along the axis z. So you can measure simultaneously x, y, and z. That is the position of a particle. So what happens if you do the measurement for two operators which commute? Commuting means that AB minus BA is equal to 0. And I just show you here a very simple demonstration. You apply AB and BR BA on an eigenstate of A. I call I alpha an eigenstate of A. So what does it mean? A alpha is equal to AI alpha. So you have this identity here. This is obvious. But now you can also write, if you write that BA is equal to AB, you can write it in this way. And now if you compare these two lines, you find that B acting on I alpha is also an eigenstate of A. So you see that if two operator commutes, the action of one on eigenvalue does not change, does not leave the eigenspace of the eigenvalue of the other operator. It means that B does not mixes different eigenvalues of A. So it means that if you make a measurement of A, you just project into the eigenspace, then you apply B, but you cannot, B does not get you outside this eigenspace. So you find, if you redo the measurement of A after that, you will find the same value. So you can measure as many times as you want A, B, B, A, you will always find the same result because they are compatible, the operators commute. So we have tried to express that. So this shows, of course, that B acting on I alpha belongs to the eigensubspace of the eigenvalue AI of A. B has thus no matrix element between different eigensubspaces of A. And by a change of basis, I can always find a basis which is common to A and B. And if I found a basis which is common to A and B, I can just express the operator in this basis. And if it remains a degeneracy, I can always imagine a third operator which commutes with A and B and which leaves the degeneracy remaining. And if I put enough operators commuting, I can finally find a vector which is unambiguously assigned to a series of eigenvalues. This is called this theory is called a complete set of commuting observables. And I will give you some examples of that later. You can always diagonalize together operators which commute with each other. And I have tried to show you what's going on here. I've taken a very simple example. I am assuming that A has 3 eigenvalues, A1, A2, and 3. And each eigenvalue is a two-dimensional space. So what if A and B commutes, it means that B has only matrix element inside each of these small squares. So B is restricted either here, here, and here. And I can always change basis and diagonalize B inside each of these squares. And I get now 6 eigenvalues which differ A1 here, A2 here, A3 here. And within the first one, 2 values of beta for I have beta 1, beta 2 here, beta 3, beta 4 here, beta 5, beta 6 here. I can always diagonalize operators which commute together. Now it's completely different if A and B do not commute. What will happen? I measure A. So I project into the subspace corresponding to one eigenvalue of A. Then I apply B. But if B does not commute with A, the projection will get you out of this subspace for A, which means that if I remeasure A afterwards, I can find any other eigenvalue of A if the operator do not commute. And this is what I have tried to show you on the right side. So you see, I make a first measurement and I find the eigenvalue A, which restricts my operator in the red box at the bottom. Now, after I measure B, again, I mix everything, and now A can be found in all the 3 boxes. So this is what happens when you measure successively non-commuting observable. A measurement of one scrambles the eigenspace for the other, which means that you don't find a well-defined result when you cross the measurements. Measuring B perturbs the probability distribution of results of measurement A. And the Heisenberg uncertainty relation between X and Px is an example of this incompatibility of measuring with arbitrary precision, non-commuting observables. And I will come back in conclusion with that. Now, what I want to discuss here briefly is what happens if you have continuous basis. Up to now, I seem to simplify, I assume that my Hilbert space is made of discrete eigenstates and eigenvalues. But we have continuous variables. For instance, if you measure the position or the momentum, it can take any value. The spectrum is not discrete. So what you have to replace the discrete sums by integrals. And this is what I have tried to summarize here. You see again that you take the projector on X, you multiply by dx, and you sum over X, you get the identity in one dimension. And the scalar product of X with X prime now become a delta function of X minus X prime. And following line, X, the operator X acting on the ket X gives the eigenvalue X times X. So you have to be a little bit careful to understand what it means. When I take a capital letter, I mean the operator. And when I take a small letter, I mean the eigenvalue of the operator. And you see now that you can project any state psi. You take here the x here, sum over x, this is the projector on x, you sum over x, and you multiply by psi. And if you look at that, what you have here is psi of x. This is a wave function. The wave function is just the scalar product, the inner product of the ket psi with the bra-x. So it's a definition of the formal definition of the wave function. And it follows that the probability to find the result x when you make a measurement is just psi x squared. This is the probability density, and this is what I have said at the beginning of the first part of this lecture. The square of psi x squared is the probability to find the result x in a given interval. Now, when you apply the operator x on psi, what do you get? Clearly, look at what happens here. X acting on the bra just give x times x. So what you find is that applying the operator x on a wave function, multiply it by x. So operator x acting on a function psi of x give x psi of x. And the same for if you take any function of x, for instance, the potential u of x, the potential in which a particle is, you just multiply psi of x by the function u of x. So you get this very simple result. On the right side, I let you do it, but you can do exactly the same thing for the operator p, which is a momentum. And now the eigenstate of the momentum are just the plane waves, and the ket, corresponding ket, is just you note it p, and you can expand the same function psi on the p's, and the expansion give you now psi tilde p, which is the representation of the same function in the momentum space. And the formula that I show you here shows that the representation in the p space is just the Fourier transform of the representation in the x space. So you can represent the same state either in the position basis or in the momentum basis, and it's a Fourier transform operation. And what it shows here very simply, what you find here is that the action of p on psi, if you want to look at it in the x basis, a very simple calculation shows that it is just the derivation with respect to x with h bar over I in front. And this is something which we already used for Schrödinger's equation. P is just h bar over I times d over dx. This is just a consequence of the Fourier transform. The Fourier transform of the derivative of a function is equal to the Fourier transform of the function multiplied by the conjugate variable. On this slide, I give briefly a demonstration, a formal demonstration of the Heisenberg uncertainty relations. What I said at the beginning of the lecture is delta x, delta p equal to h bar. But I did not define exactly what I mean by delta x and delta p. What is the standard value of this uncertainty? And this is what I try to do here. First of all, at the top of this slide, I give a demonstration of the commutation relation between x and p. You see, this is the commutator of x and px. And I take it inside the function. So I take x, px, I act it on psi, and I look at the wave function by taking the brackets x. So I get this expression here. And you see now that this does not commute because it's not the same thing to multiply a function by x and derivate, or to derivate and then multiply by x. And so if you do the two operations, what you find very simply is that you find I h bar psi x. So you see that the commutator is equal to I h bar. xp minus px acting on any function psi give you I h bar, this function psi. So the commutator value is I h bar times the identity operator. So now what I would call, what is a standard deviation? You take an operator and you subtract from this operator the average value. So you get an operator which is, of course, centered around 0. And if you take the average of this x prime operator, you will find the distribution of values of x. So the square, this is the square of x prime, is what we call delta x, delta x squared, the standard deviation, and the square of p prime, which is the operator minus its average value, give you the standard deviation of p squared. So this is a formal definition. This is a standard deviation. This is the width of the distribution squared. Now, for any ket psi, what you can do, for any ket psi, you can form the ket x prime minus I lambda p prime, where lambda is any real number. So I just take this operator and I apply it on the ket psi. So I get a new ket, which I call capital psi. And now I compute the norm of capital psi. So look at what, fortunately, my laser does not work anymore, but so you have here the quantity x prime minus I lambda prime time x prime plus I lambda p prime. And I remind you that when you act on the bra, you have to take the conjugate. So this is what you get. And if you develop this, you find x prime square plus lambda p prime square plus I lambda times the commutator. But the commutator is equal to I h bar. So you get the bottom line of this slide. And at the bottom, you find that the norm of the vector psi is equal to delta x squared plus lambda squared delta p squared minus lambda h bar. But this is the norm of a vector, so it has to be positive. And it has to be positive for any lambda real. So the discriminant of this second order equation has to be negative, because if it's positive, lambda will cross the value 0. There will be a value for which it will cross the value 0. And if you write that the discriminant is negative, you find delta x, delta px larger than h bar over 2. So the real standard form of Heisenberg uncertainty relation is that delta x, delta p has to be larger than h bar over 2, not h bar. So you see that how, just as an example, how a very simple calculation using the Dirac formalism gives you this kind of result. And you can use that now, this expression, let you do it at the bottom of this slide, to show that the harmonic oscillator has a minimum energy. And it's what I said before. If you try to decrease p squared, you will increase delta x squared. And the compromise is that you stay with fluctuation of position momentum. And the fluctuation of position gives a delta p square of h bar omega over 4. The fluctuation in momentum also. So you have an energy, a 0-point energy of h bar omega over 2 for any oscillator. So the potential and kinetic energy of ground state are both equal to h bar omega over 4, and the total energy to h bar over 2. And this is due to the non-commutation of x and px. Now, what I have said about the wave function, I can expand this and find again the Schrödinger's equation with this point of view. You see, the Hamiltonian of a particle is just p squared over 2m with a capital P, which is a momentum, plus u of x, a capital X is a position operator. And this Hamiltonian p squared over 2m plus ux is the energy observable. If you write it in the x representation, so you take h of psi and you put the bra x, you find the form, usual form, minus h bar squared over 2m, second derivative is x plus ux psi x. So this is exactly what Schrödinger had found with his wave function. Now, the eigenstate of the Hamiltonian, these are the energy state of the particle. And they satisfy by definition h psi is equal to e psi. This is the definition of an eigenstate. But h psi is also IH bar d psi over dt. So you find that an eigenstate is simply evolves simply with an exponential term e minus IE t over h bar. So if you are in an eigenstate of energy, this state remains stable. The only thing which changes is the phase. It means that if you have now in a superposition of energy states, each state of a superposition will have a different phase. So the distortion of phase from state to state will give the time evolution. The system will evolve in time if there are two states of different energies, because the amplitude of each state will change. The phase of each state will change as a function of time. Now, if you want to solve this, the Schrödinger equation and find the energy state, you have to solve the equation written here. You apply the Hamiltonian, and you say it's equal to E times psi. And this is called the eigenvalue equation. And in quantum physics, there are two problems for which you have an exact solution. You can solve this equation for the hydrogen atom, and you find a spectrum which is exactly the spectrum of Bohr. So Schrödinger equation gives exactly Bohr spectrum. And you have to understand also that each energy state has a degeneracy. That's why I put other quantum numbers. This is an example of what I said before, because the Hamiltonian commutes with the angular momentum and with a component, any component of the angular momentum. So you have a set of eigenvalues, energy, angular momentum, projection of the angular momentum, and these states are all degenerate. And this is a spectrum that Bohr had found for the. Bohr has only studied the circular orbit, which has the largest angular momentum, so he did not discuss the degeneracy. The other problem, which has an exact solution, which is the harmonic oscillator. And when you solve the harmonic oscillator, what you find that each direction, each degree of freedom, x, y, or z, is a 1D oscillator, which has a spectrum of eigenvalues proportional to n. It's like the field mode. N are the vibration quanta, which are like the photons for the electromagnetic field. And you have this in each direction. So for a 3D oscillator, you have nx plus ny plus nz plus 3/2, which is the fluctuations in 3 directions. And you have this simple spectrum. Finally, finally, on this slide, I just look at the operators that we have introduced in a different perspective. What I show here is that the Hamiltonian describes the translation in time of the state. The momentum describes the translation in space, and the position operator describes the translation in momentum. And this is what I try to show you here. For that, I need a last definition. What is the function of an operator? What does it mean to consider the function of the operator O? There is a very simple definition. You go in the basis in which O is diagonal, and f of O is just the operator which has the same eigenstate, but with the eigenvalue, which is the f, the function applied on all the eigenvalues. So it's just a function of an operator is very simple to define once you are in the basis in which the operator is diagonal. So let's look at what happens, for instance, for the Hamiltonian. What you have seen is that applying, looking at the time evolution of an eigenstate, you just have a phase factor. So now if you look at the most general state, it will be a superposition of states with different eigenvalues. Each of them will have its phase factor. And you get very simply what I've written here. You find that psi of t is just the action of this operator, which is E minus I h t over h bar acting on any psi. So this operator is the exponential of the Hamiltonian is just the evolution operator, the operator which describes how the wave function is translated in time. In the same way, you can look at an exponential operator of P with here a parameter x0. So what is this operator? And with these two lines of calculation, I show that this operator active on psi x gives psi x minus x0. So it just translates the state along the x0 axis. And finally, you can look now at the same operator now, which is an operator of x with a parameter p0, and you find that this translates in momentum space. It takes a system and give a kick corresponding to momentum p0. So this summarizes the fact that the generators of translation in space, time, and momentum are the Hamiltonian, the momentum, and the position operators. And we will see next week that the generator of rotation, the operators which rotate the quantum state, are the angular momentum operators. So I conclude now. These are the important final notes. So I remind the importance of De Broglie, of the Heisenberg matrix description, the importance of the concept of complementarity and the uncertainty in measurement, and the fact that the theory is essentially probabilistic as opposed to the absolute determinism of classical physics. And then I summarize all the results that I have shown to you in the second part of the talk. And the important point is that the measurement perturbs in an irreversible way the observed system state, making it possible to determine with precision the values of observables which are described by non-commuting operators. Now, what I have not discussed up to now, I have told you the postulates of measurement, but I have not shown you what is in practice a measurement. When you do a measurement, you have to couple your system to an apparatus and study the evolution of the two and try to find information from the apparatus about the system. It has to respect these postulates, but I think we have to describe what we do in a measurement in a more precise way so that you can get a better feeling of what the measurement is about. And I will discuss that next week. I will continue to discuss the basic concepts and their physical implication. In particular, I will discuss the problem of the spin, angular momentum and the spin, and show you that on a spin system, you can make exercises, make calculations, which show you in practice what the postulates mean. And so we'll do that next week. And I will stop at this point. Thank you.